Welcome everyone. So today, we'll explore the Boy-Moore majority vote algorithm. This is a powerful technique used to find the majority element in an array. That is, the element that appears more than half the time. The great thing about this algorithm is its efficiency. It runs in the linear time, meaning it goes through the list just once, and uses constant extra space, which means it doesn't require any additional memory regardless of the input size. We'll look at how it works, walk through Java code, and understand why it's so effective. Here, the number 3 appears 5 times out of 7, so it is the majority element. Understanding this definition is crucial because the algorithm only works if such an element exists. Keep this problem in mind as we move forward.
Before we dive into the Boyer-Moore algorithm, let's look at some straightforward methods you might think of. One is sorting the array and then returning the middle element. This works because the majority element will definitely be in the middle after sorting. However, sorting takes O of n log in time, which can be slow for large datasets. Another approach is using a hash map to count the frequency of each number. This gives us linear time that uses extra memory proportional to the input size, which isn't efficient. So, this method have trades-off that Boyer-Moore algorithm cleverly avoids.
The Boyer-Moore algorithm solves this problem efficiently in two phases. The first phase is the candidate selection, where we scan through the array and find a potential candidate for the majority element. The second phase is verification, where we count the occurrences of that candidate to confirm it is indeed the majority. This method uses a smart voting mechanism to balance counts, which lets it find the candidate in just one pass while using constant memory.
Our algorithm has excellent performance. It runs in the linear time O of n because it makes just 2 passes over the array. One to find the candidate and one to verify. It also uses constant space O of 1 as it only keeps track of 2 variables regardless of input size. This makes it ideal for very large datasets or systems with limited memory.
We begin by initializing two variables, count set to 0 and candidate set to none. As we traverse each number in the array, the count is 0. We assign the current number as the new candidate and set count to 1. This step signifies that we're considering this number as a potential majority candidate. When the current number equals the candidate, we increment count by 1, indicating increased confidence in our current candidate. When the current number differs from the candidate, we decrement count by 1, representing a vote against the current candidate. This mechanism effectively balances out counts between the candidate and other numbers. If a majority element exists, it will remain as the candidate after this progress, as its frequency surpasses the combined frequencies of all other elements. After identifying a candidate, we cannot immediately assume it's the majority element. We need to verify it by going through the array again and counting how many times this candidate actually appears. If the candidate's count is greater than half the length of the array, then we confirm that it's the majority element. If it doesn't meet this threshold, we return -1 or to signal that no valid majority element exists. This extra verification step is crucial. It guarantees that the algorithm only returns a valid majority when one truly exists, making sure that the result is always correct. Let's walk through an example using the array 1, 3, 3, 1, 2. So, we start with the count 0 and no candidate. First number is 1. Since count is 0, we set the candidate to 1 and increase the count to 1. Next number is 3. It's different from the candidate, so we decrease the count to 0. Because count is 0, we reset. The next number is 3, so we set the candidate to 3 and increase the count to 1. The next number is 1. It's different from the candidate, so we decrease the count to 1. Again, count is 0, so we reset. The last number is 2, so we reset the candidate to 2 and increase the count to 1. By the end, our candidate is 2. But now we need to verify. We count how many times 2 appears in the array, so let's go back and check the array. So As we can see, the 2 only appear once. So since 1 is not more than half of the array's length, we do not have the majority element.
This algorithm isn't just for academic problems. It has practical applications like finding popular trends in data streams, which is useful in social media analysis or network monitoring. It is also helpful in voting systems to find consensus and in distributed computing for leader election. Basically, whenever you need to find a majority or a leader efficiently, Boyer-Moore is a great tool to use. To summarize, the Boyer-Moore majority vote algorithm efficiently finds the majority element using a clever voting system. It runs in linear time and constant space, making it very efficient for large datasets. It works in 2 phases, candidate selection and verification. This algorithm is not only important for coding interviews, but also has many real-world applications.